Today, we're doing another LeetCode session where I solve random LeetCode problems without any preparation. Just my actual thought process, the things I try, what works, what doesn't. But before we start, I wanted to quickly address a question someone asked on a previous video. Why I use Python for these instead of C++. So here's the honest answer. I don't actually like Python for working on big projects. It's not type safe. Everything is very simple and loose, and for building actual software, I prefer a more structured language. But for LeetCode, the simplicity is exactly why it's perfect. LeetCode and DSA interviews are all about your thinking and how you break down the problems, and Python cuts out most of the boilerplate and lets you really translate your thoughts into code pretty easily. It's basically as close to English as you can get with code. Most interviewers won't bat an eye if you use Python, and from what I've seen, it's pretty much the standard now because it really lets you focus on the logic rather than the syntax. So, with that said, let's get into it. Okay, let's start with the daily question, as always. You're given a binary array nums, 0 indexed. We define xi as the number whose binary representation is the subarray from most significant bit to least significant bit. Okay, with binary, I always get mixed up. Which one is the most significant bit? I'm in digital logic right now, and this has been the single biggest point of confusion. Leftmost bit, highest positional value. Okay. That's what I thought. Just double checking. So x0 is 1. Find xi is the most number whose binary representation is the subarray of 0 to i. Okay, so it's 1, it's 2, and it's 5. Okay, interesting mechanic. Return an array of booleans answer where answer I is true if xi is divisible by 5. Let's just look at some examples of binary numbers that are divisible by 5. So 5 is, that's 5. 10 is going to be 8 plus 2. Okay. 15 is going to be, is it that? Yeah. And then 20, 16 plus 4? Well, okay. I'm not really seeing a clear pattern right now, just looking at it. So my first thought is just take each subarray, convert it into decimal, mod 5, and then decide. I mean, it is an easy problem. Probably shouldn't overcomplicate it. Okay, I'm gonna just write it out. So we're gonna make the binary be a string, and then yes. I mean, I don't work with binary very often in Python, so good to know. Yes, so we want a string. So our binary string is going to be empty, and then for each item in nums, we're going to append to the string, convert that string to a number, and then mod 5 it. And then we want to have the index in nums so that we can add it to a resulting array where we have just booleans. I think we might have to convert that to string. Yeah. Okay. Oh, we forgot that. Result. Okay, it's working. Let's see. Okay, let's go. Except the runtime is kind of horrible because there's probably a better way to do this other than just converting it around. Okay, I'm actually going to look at the topics just to see. Okay, bit manipulation. I think it's one of those things. It's one of those binary bit manipulation I don't see very often, so I'm not super practiced, but now's a good time as any to figure it out. So is there a bit mask of some kind that we can apply to see if it's divisible by 5. When we talk about being divisible by 5 when we are a binary number, what does that actually look like? What are we seeing? 0, 1, 1, 0, 1, 1. 0, 0, 0, 1, 1, 0. Holy crap, man, this is difficult. This is supposed to be an easy question. Well, I guess I did solve it pretty easily, but making it better is actually what the hard part is, which tends to be the thing for most questions. Again, it's not necessary for me to figure out how to make this better because I did solve it and it was accepted, but I like to challenge myself and see if I can get the most optimal result. Okay, I think this is some sort of bit mask trick, and I have not worked too much with bit masks, as I said, so I am going to I want to see what people did to get 22 seconds of runtime. Okay. Never mind, we can't look at that. Somebody cheated. Let's look at that. Okay. So we have an answer list and b equals 0 for a in the list. We shift in a 1 into b. Oh, it shifts the bits by 1. Okay, so if we shift it once, it's 1, 0, 1, 0. Okay, so we're shifting b by 1 to the left. So we're doing it bitwise OR with a. Oh, I see. I see what's happening here. We're doing bitwise operations on the integers as though they were binary, but they are binary under the hood. So we can just work with that without having to convert to string and back. Yes, because I was converting it to a string and then converting it back to an integer when we didn't actually need to do that because we can just shift each one in to the integer using bitwise operations. That makes perfect sense, so that is perfectly simple. Yeah, well, that just goes to show not every LeetCode session is about practicing your skills. Sometimes you learn new things, and that is okay. Okay, let's try it. The binary, we're just going to say it's a 0 for now, and result. And for each one, we don't even need that. Yeah. Oh yeah, we didn't need that in the first place because we just append. We don't need to have the index. Yeah, okay. For n in nums, we want to shift in. It's shift it down 1 and bitwise OR the new number because we want to add it at the very end. So we shift it over 1 to the left and then stick in that last num because n is only ever going to be 0 or 1. So we either stick in nothing or we stick in a 1. And then we don't need to convert that. We just do that. Perfect. There we go. Much better runtime. Yeah, look at that difference. No need to mess around with strings. Do it the proper computer way. Speak the computer's language, aka binary. All right, so for the next problem, I'm gonna switch things up and I'm gonna stand. Which brings me to today's sponsor, FlexiSpot. I've been using their E7 Pro standing desk for the past couple of days, and it has definitely been an upgrade. One thing I didn't realize until I tried it is just how much changing positions helps with focus. As a CS student, I spend so many hours glued to the computer screen, and getting to stand up and move around, I was skeptical at first, but it has actually been really helpful. And you know what they say, sitting is the new smoking. One of my favorite things about this desk is just how easy it is to adjust the height. It has a huge 25 to 50.6 inch range, which you can adjust with this touch keypad, and it even has set height presets. And okay, I had to try this. This desk can hold up to 440 pounds, which is kind of wild. FlexiSpot also offers a 15-year warranty on the E7 Pro and a 30-day return window in case you change your mind. And right now, they're running their big Black Friday sale with up to 80% off. And if you use the code here on the screen and down in the description and mention Anna Codes when you check out, you can get an additional $30 off. All right, let's do another one. Given an array of positive integers nums, remove the smallest subarray, possibly empty, such that the sum of the remaining elements is divisible by p. You are not allowed to remove the whole array. Return the length of the smallest subarray you need to remove, or -1 if it's impossible. Okay, so 3, 1, 4, 2, that the sum of the elements is 10, which is not divisible by 6. We can remove the subarray 4, and the sum of the remaining elements is 6, which is divisible by 6. Okay, so then 6, 3, 5, 2, that's 9, 14, 16, not divisible by 9. We cannot remove a single element to get a sum divisible by 9. The best way to remove the subarray 5, 2, leaving us with 6, 3, with sum 9. Therefore, we have an output of 2 because it's a length 2. Okay. Well, before we get into seeing what the smartest way to do this is, let's think about the brute force solution. The brute force solution would be to first we check if the sum of the array is already divisible. Then we check every single number. If we take it out, will it be divisible? And then if not, we check every 2, every 3, and so on up until the entire array. Well, n minus 1, where n is the length of the array, because we're not allowed to remove the whole array. Okay, let me grab my comment template. There, we like to have that, just to have somewhere to put my thoughts and kind of walk through it intentionally. The brute force solution, would it be O of n squared, where n is the length of the array, because we first have to go through it once to sum it, then another time, so we'd have to go 1, then we go through it again 2 for each 1, and then we go through it again 3 for each 2, and we go through it again 4 for that. So I think the brute force solution is O of n squared. How can we make this better? Okay, well, the word subarray here makes me think sliding window pattern. I'm not entirely sure if that's the best way to do it, though, because we have the sum of the numbers, right? And then it's either divisible or it's not. And if it's not divisible, then there would be a remainder. We would divide it and there would be a remainder. That remainder is what we want to remove. So if there is an element that adds up to the remainder, if there is an element that is the remainder, we could remove that. Or if it adds up to the remainder. Right. So would that be an improvement if we just say, okay, first we check if the sum is divisible. If it is, we just remove 0. If it's not divisible, then we get the remainder. And then the remainder is the number that we kind of want to check against for the remainder of the problem. Yeah, so basically after that, we just want to find a subarray that adds up to the target. I mean, this is pretty close to what we were talking about in the first place, but okay, well, it's a little bit better than the brute force because we're not recalculating every single time. Okay, we remove, then we get the sum, then we divide and see if it's possible. We've skipped that part. We already know exactly what we want, and that is for the subarray to add up to the remainder. We go through it once, checking the 1s. We go through it twice, checking the 2s, and so on and so forth, until we either find an answer or we look at the 2 n minus 1 arrays and we do not find it. That's a little bit better, but it's still O of n squared. I'm just going to take a peek at the topics to see if there's maybe anything else. Hash table, okay. And prefix sum. I mean, there's probably multiple different ways to approach this, and they all have different trade-offs. So yeah, so I think we have one approach that we could do. How would you use a hash table, though? Nothing is coming to mind about using a hash table, but the prefix sum does make sense because we are trying to find sums of the subarray. So how can we use a prefix sum? We can make a prefix sum array, and then we can iterate through. Let me just try to visualize this for myself. So for this array, the prefix sum array would be, okay, and then we know that we can remove 4. So let's say, okay, we've gotten through the step where we say, okay, this is not divisible. We go through each one and kind of say, okay, oh, right. So what is our remainder? The sum is 10, which is not divisible by 6. Remainder is 4. So we need to remove a 4, or actually, to be more general, we need to remove 6 times n plus 4. N being any integer, including 0. No, any positive integer or 0. Okay, but for this one, we only need 4. So our best case scenario is that we only need to remove one of the elements. So we would probably want to first iterate through the regular array and say, okay, 3 doesn't fit, 1 doesn't fit, 4 fits. We can return 1. But if we get to the end of this and we say something like this, yeah, I'm going to just redo this. So then we would say our sum is 16. It's not divisible by 9. The remainder is 5. No, 7. Sorry, the remainder is 7. And our goal is 9. So we want to find something that is 7. Let's see, this 7, no, 7, no, 7, no, 7, no. Okay, then we go on to the pairs. We'll say we skip 0, we go to 1. Is that 7? No. And then we go this, and then we want to do that minus 6, which is 8. 8 is greater than 7, but doesn't have 9 times n there. Okay, so we can't do that. So 16 minus 9, that's 7. And that is our answer then. So the subarray ends at 16, or not 16, it ends at index 3, okay, here. And it starts one before that because we are looking at the 2 pairs right now. So that's why we went 16, then go 2 down, minus 9. That's how the prefix sum works. Obviously, if not, we would start with, instead of this one, not this one, we'd start with this one minus nothing, then that one minus that one. Okay, so that would be our subarrays of length 3, which is n minus 1, which at that point, if we hadn't found anything, we would return -1. So at this point, worst case is still O of n squared, because we have to go through the prefix array O of n times. The prefix array is n length. Which makes me think, am I correct in saying that the brute force is O of n squared? It still might be, because a lot of times you do make major improvements in the code, but it doesn't actually change the time complexity, because the time complexity isn't something that tells you exactly how efficient or not efficient something is. It just tells you what curve it follows as your input gets bigger. So just because one solution is O of n squared doesn't mean another solution that's O of n squared isn't better or worse. So there is a lot of leeway, even within one time complexity, technically. Okay, what is our approach to solving the problem? I like to type it out in English first, just to make sure we're really, I want to say on the same page, but I'm not really working with anyone here right now. It's just kind of like my problem-solving brain is on the same page as my syntax writing brain, if that makes any sense. Okay, so first, check if sum is divisible. If yes, return 0. We don't need to remove anything. If no, move on. Then we check if, no, we make the remainder. We figure out what the remainder is. Check if it is in the array. If it is, return 1. If not, move on. Make the prefix sum array. Iterate through, starting with 1, subtracting I minus 2, right? Because it's 14 minus 6, and then 16 minus 9. If found, return 2. Repeat previous step until n minus 1, where n is length of array and I minus n minus 1. So we keep incrementing this until n minus 1. If still not found after that, then return -1. Okay, that is a time complexity of, I believe, O of n squared, and space complexity, we are making a prefix sum array, so we need an additional O of n space. Okay, first we check if the sum is divisible. If sum of nums divided by p equals 0, return 0. Otherwise, we go make the remainder. The remainder is, actually, the remainder is 0, return 0. If the remainder is in nums, return 1. Otherwise, let's make the prefix sum array. Sum of nums to I plus 1 for I in range length of nums, I think. right? Because for 0, it'll be up to 1, up to but not including, because that's how list slicing works in Python. So range length nums goes up to, for example, 4. If it goes up to 4, so we want to go up to 5, but that doesn't exist. In fact, even 4 doesn't exist. Okay, so we actually want to go -1. I think that's how you do it. It's been a while since I've done prefix sums. How do we do this? Just to make it simpler for ourselves and really understand what we're doing, let's write it out for a subarray of length 2 first, because that's what we're doing first. And then after that, we'll generalize it to be able to do it up until n-1. For I in range of nums, except we want to start with 1. So for example, let's get our example down here. I want to start with 1 minus be -1, but it wouldn't be. Let's preprocess the I to say we want to subtract the proper thing, except if it's 1, we're not going to. And then later on it'll be if it's 2, we're not going to. If it's 3, we're not going to. But it is actually, we're not doing 3. Never mind. You get the idea. If I is not equal to 1, then we want to go, if I is not equal to 1, oh, we can't reassign I because I is the index. We want to assign the number. So the number is nums I. If I is not 1, then num is actually going to subtract I minus 2 from it. Then num is equal to remainder, return 2. And then if nothing works, return -1. So I don't think in our test cases we have anything longer than, well, let's just try it. It's not going to work for any case where it needs a subarray of longer than 2, but let's see if it works for subarrays up to 2. Yeah, so we only need 1 there. I think that's an example. And then 1, 2, 3, that's already good. We don't need to return anything. Okay, for this one, we are saying that no, when we can actually do that. The first thing I want to double check is to see if I actually made my prefix sum array correctly. So I'm actually gonna go ahead and bring this into VS Code. Okay, and let's just turn off Copilot, just to make sure it doesn't give us the answer too quickly. And we see the answer right away. Prefix isn't being used. We're using the wrong array. Okay, let's try it. Right, because nums -1 actually. Okay, still not. Wait, no, it shouldn't be. No, it should be like this. Because it's not, the end is not included. Let's bring this back into VS Code, see what's going on. Again, I want to check it to see if the prefix is being done correctly. Why is Copilot on? Okay, you better not give me the answer. I'm not trying to be taken over by the AI overlords. I want to practice my brain once in a while. After that, side note, what are we having an error with? Where nums is that and p is 9. So we want to have solution min subarray, and then we want to go the nums are that and p is 9. Our prefix sum is too long. Why are we doing that? There was a reason why I wanted to do that, but it's not correct. That's what we want, right? Yeah, that's exactly what we want. Did a little bit of a miscalculation with the range endpoints there. Okay, there we go. So that's working. Now we want to think about if we end up needing a subarray bigger than 2, because what's the length of the nums? Up to 10 to the 5. Okay, we want to go for, I'll say n in range. We start from 2 and we go up to length of nums -1, because that's what we said up here. We said up to n-1. That's our n then. And then it's actually going to be n-1 because when we had 2, we wanted 1 because of 0 indexing. Okay, so we do that. If I is not equal to n-1, then we go I minus n-1. No, it's n. I minus n. Wait a minute. Range is exclusive, right? The range endpoint is exclusive. It's not n-1, it's up to the length because we want to go up to length -1. So our return n. Let's see if that still works. No, because I forgot a colon. Okay, now it works. Okay, so now I believe it should work for all cases where this n right here is 0. because we haven't actually checked for when we remove the remainder and a whole extra of the divisor. It's either dividend or divisor. Is it divisor? This is like, I haven't thought about this since like middle school. So yeah, it'll work for all cases where n here is 0. It probably won't work for everything, but I just want to double check. Yes, indeed. So most of the test cases have passed, but quite a few haven't. And I'm willing to venture to bet that this is not. So if num equals r or num mod p, should we do or? I don't think we need it. Because, okay, mathematically we don't need it. I'm just thinking optimizationally we can say, oh, most of the time it will be this or that, but I don't think it's that much of an optimization. Let's just do that. Yeah, that was actually easier than I thought it would be. Okay. The output there is 4, and we expect it to be 1. We expect it to be 1 because we expect r to be in nums. Because r might not be in nums, but r plus that might be in nums. Okay, if r in nums or r in n mod p for n in nums. Yeah, because then that or prevents it from running unless it has to. Because if r is in nums, then it won't run this. It will just say, okay, this is true, so we don't need to bother about this. We can just do this. If it's not true, then we go through the trouble of making that list. Then, technically speaking, afterwards, we can just always use this instead of doing this. Something to think about if we want to go back and optimize. For the meantime, let's just try to get all these test cases passing. All right, time limit exceeded. So clearly we need to optimize before we can get all our test cases passing. Okay, so none of these are bigger than this, are they? I think all of these are 5-digit numbers. Yeah, I wanted to know how long the numbers in the input were, because if they're larger and we're summing them up and things like that, if we modded them down just to be the remainder of p, might make calculations faster, but yeah, but I don't think that would work. Well, I'm just gonna look at the hints. Yep, we did that. Yep, we considered that. Just removing the subarray effect that remainder. Yeah, the sum of the subarray that we remove has to have the same remainder as the remainder of the full array in order to make it divisible. Okay, hint 3. Use a map to keep track of the rightmost index. I just realized this is where we might be running into issues with really, really big numbers, because in the prefix sum, we only ever really need to have it be that, and then we don't need to worry about that there. Let's see if that makes it any faster. I doubt this will make the entire difference, but we have a wrong output. Why not just keep that in? Once again, time limit exceeded. And I think it was on 1 fewer test case. Didn't really help. Okay, let's go back to the hint, because they said something about maps that we haven't quite implemented yet. A map to keep track of the rightmost index for every prefix sum. What does that even mean? The rightmost index is just the index of the prefix. Now, here's the thing. Like, I'm getting it right. It's just that there's a time limit that is getting exceeded. And as a matter of fact, let me actually put this back into VS Code just to make sure that it's the time limit being what it is that is making it exceed and not an infinite loop, as time limit exceeded sometimes is. Okay, yes, we know there's a lot. I dare you to make this work. So that took a while, longer than LeetCode wants, I guess. So we do need to use the map thing, I think. But the problem is, I don't quite understand what they mean by use a map. An O of n squared method leads to time limit exceeded, yes. An array method with prefix sum leads to, what's Emily? Oh, memory limit exceeded, yeah. Honestly, people are saying this is not medium, and I agree, because I think my solution does work, is the thing. It's just that for this particular question, LeetCode does want a certain optimal solution, without which it won't even accept my code. I'm still not really understanding the whole idea of using a hash map on top of everything here, so I'm gonna try to find a solution that explains this. Yes, that is what we figured out already. Find the shortest subarray whose sum mod p equals the remainder. Okay, so we're doing a little bit of math here now, okay. No, okay, I think that I'm starting to get it. So we have what we have gotten to. We algebraically rearranged this to say there is a relation between one part of the prefix array with another one. So then we go through prefix array and look at the hash map and try to find it. Okay, and then at that point, we get an O of n space complexity because we just had to go through the prefix array once. Well, not once, but a certain constant amount of times to make the hash map and then to actually go through it. Since we go through a prefix array a certain constant number of times as opposed to n times, it's still O of n. That is better, even in terms of type complexity, than mine. However, I don't want to make this video like 2 hours long, so I'm actually going to stop here and not implement the hash map solution. All right, so I think that wraps up today's LeetCode session. As a reminder, if you want to check out the FlexiSpot E7 Pro standing desk that I used in this video, the link and my code are down in the description. And if you're new here, I'm a CS student sharing my journey to becoming a software engineer here on this channel. So if that's interesting to you, feel free to stick around, and thanks for watching.